Hi, my name is Brian Schwedock, and I'm going to talk about near-data computing for general-purpose systems. This work was done at Carnegie Mellon in collaboration with my advisor, Nathan Beckman. It is well known that the cost of data movement keeps getting worse. This graph compares the relative speedup over time for both processors and memory. Processor speeds have improved orders of magnitude faster than memory, a trend known as the processor-memory performance gap. And energy shows a similar pattern. This graph plots energy for an arithmetic operation and different types of data movement. As you can see, the energy to access data in memory is orders of magnitude more than compute. In response to the growing data movement challenge, near-data computing has become a popular design choice. NDC can significantly reduce data movement by computing on data where it resides. After reviewing the wide array of work in this field, we have identified that most NDC proposals fit within 4 common design paradigms. With task offload, a core explicitly offloads a short computation closer to data in the hierarchy, and often returns data back to the core. Long-lived workloads involve a long-running task executing closer to main memory, often to avoid polluting the core's private cache. Data-triggered NDC involves computation triggered when data moves across levels of the memory hierarchy. And streaming involves a decoupled producer running in the cache and feeding data to the core. Each of these paradigms has demonstrated the potential for significant data movement savings through proposed NDC systems. So what's the problem? Although there are so many NDC proposals, each targets a limited application domain while requiring its own hardware and software support. Even programmable systems, such as Livia, DistDA, and Taco, only support the ability to implement a subset of NDC optimizations. No prior system is able to support all 4 common NDC paradigms. That's unfortunate because there are major challenges with systems only supporting limited paradigms. Developing new hardware for each NDC optimization is not a scalable solution to the data movement bottleneck. CPUs are so widely employed because they can each run almost arbitrary software. New NDC hardware typically requires new programming interfaces, so each new design places more burden on programmers. Supporting all paradigms on the same system also allows rapid development of new NDC optimizations on a single platform. Finally, some NDC optimizations require support for multiple paradigms to achieve their full potential. I'll demonstrate one such example later in this talk. Another drawback of prior systems is that programmers are forced to reason about microarchitectural parameters for each system they use. Now, what do I mean by this? As an example, imagine an array of 24-byte objects divided into 64-byte cache lines. Many objects will be split across 2 cache lines. This is a problem with distributed caches because contiguous cache lines often map to different banks. As a result, near-data tasks can only execute near part of the object, losing locality benefits from near-data execution, or requiring programmers to carefully pad and align data. And what about objects larger than a cache line? They will almost always span cache banks, forcing programmers to limit objects to within a cache line. Thus, prior NDCs require programmers to reason about cache line size, which is an unnatural and limiting interface. To overcome these issues, we propose Leviathan, a unified system for practical near-data computing. Leviathan supports all 4 NDC paradigms discussed earlier on the same system. It does so by incorporating a near-data engine on each tile of a multicore processor, which has microarchitectural support for multiple paradigms. And to alleviate the issue of hardware abstraction, Leviathan provides an object-oriented programming interface and then performs all data management invisibly to the programmer, ensuring that near-data actions always have their data locally. To help describe Leviathan's design, I'm first going to show an example application that benefits from near-data computing. Linked lists are a simple yet very common data structure. To find a given node's data, a thread must traverse the linked list, one node at a time, until the desired data is found. Let's look at the data path for a normal linked list traversal where the data is spread across the last level cache. The thread needs to pull each node from the remote cache banks into the core one at a time. Each node incurs a costly round-trip traversal over the on-chip network. Now, let's see how task offload can improve the traversal. This time, the thread offloads a lookup to the location of the first node, which itself offloads the next lookup, and so on, until the data is found and returned to the thread. As we can see, each lookup only incurs a single network traversal, significantly reducing the total amount of network traffic and lookup latency. Having seen an example NDC application, let's now look at how Leviathan supports NDC, starting with the programming interface. We first look at the core's point of view. For NDC paradigms that return data to the core, we provide a future mechanism, which is simply a structure that provides the data to the core when it's available. Let's walk through the linked list example. When a core offloads a task using invoke, it's provided a future, and I'll explain invoke in more detail later. The core then waits on the future until the result is ready. The offloaded task can invoke another, which then sends the future result back to the core, waking up the original thread and providing the result. And although this example only shows task offload, streaming also uses futures. The crux of Leviathan's programming interface are actors, through which all paradigms are implemented. An actor is a type that combines data with near-data actions that may operate on the data. In this example, an actor is a node in a linked list containing a key, value, and a node pointer. The near-data action for this actor is a lookup, which checks whether a key matches the node's value. If the lookup finds the key or reaches the end of the list, it returns a value that is sent back to the invoker's future. Here we see how a core explicitly invokes the near-data action using task offload with the invoke keyword. And notice that it's possible for actions to trigger further actions, as is necessary with pointer chasing. Another critical component of Leviathan is its memory allocator. The interface is very simple, just two malloc-like allocate and deallocate methods. The important point is that the allocator is the way in which applications inform Leviathan of the data access granularity, enabling Leviathan to perform all data management behind the scenes. Earlier, I showed why it's important for objects to not split across cache lines. One of the roles of the allocator is to automatically pad objects to avoid the splitting. Later, I will also show how we enforce locality for objects larger than a cache line, with additional hardware support. And importantly, objects are only padded in the cache. See the paper for details on compacting objects in main memory. Now, I'll briefly describe how to program each paradigm. I'm going to show simple pseudocode for brevity, but we've implemented them all in C++. First, task offload and long-lived are programmed similarly. There are minor differences, such as long-lived being less likely to return a value, but they both involve a core or action explicitly triggering another action. Beneath the example actor, we see how an application can allocate an actor instance and then invoke an action, which sends the computation into the memory hierarchy. Next is data triggered. We take inspiration from the prior NDC system Taco, which observed that allocating and deallocating data on cache insertions and evictions can implement a variety of data-triggered NDC designs. Accordingly, the actions for data-triggered actors are constructors and destructors, which are triggered on cache operations. Finally, streaming involves an actor with separate producer and consumer interfaces. GenStream is the near-data action, which must be implemented to populate the stream using the push function. And then the consumer, running as a regular thread, pops off the stream using the next function, which returns a future that contains the data when available. Next, I'll discuss Leviathan's architecture. Leviathan starts with a baseline multicore processor. On each tile, Leviathan adds an engine to execute NDC actions. To minimize data movement for actions, the engine connects directly to the L2 and LLC bank on the same tile. The NDC paradigm determines which cache is accessed. The engine is similar to other NDC systems, with compute logic, private caches, and state for NDC actions. The main difference is that Leviathan provides microarchitectural support for each NDC paradigm. The task offload scheduler executes an offloaded action if the data is cached locally, and forwards the action if not. The data-triggered scheduler maintains a buffer of actors currently being constructed or destructed, and determines which action should be executed on cache insertions and evictions. And the stream scheduler maintains head and tail pointers to a per-stream buffer for each stream, which is stored in shared memory. I already showed how Leviathan's allocator pads small objects to map to a single bank, but mapping objects larger than a line requires additional hardware support. For distributed caches, the bank which an address maps to is determined by hashing the address. So for objects spanning cache lines, those lines will likely hash to different banks. Leviathan ensures that large objects all map to the same bank by providing the same input to the hash function. Leviathan adds the object size to the data's TLB entry, so that the least significant bits of the object's address can be zeroed out. For this example, with objects spanning 2 lines, only 1 bit needs zeroing out. As a result, each cache line address for an object provides the same input to the hash function, ensuring that large objects map to the same bank. Leviathan's remaining architectural mechanisms include compressing padded data in main memory and additional minor per paradigm support. In total, hardware overhead, including the engines, is a little over 6% compared to the last level cache. Now, let's look at Leviathan's quantitative benefits through 2 case studies. We evaluate Leviathan in cycle-level simulation. Our system consists of 16 tiles, each with an out-of-order core and a Leviathan engine. Similar to related work, we evaluate the engine's compute logic with a data flow fabric of processing elements. Although Leviathan isn't restricted to any specific compute type, data flow fabrics have been shown to work very well for NDC actions, which execute frequently and have a small instruction footprint. Finally, we compare Leviathan to a version with ideal engines that have infinite free compute. The first case study demonstrates the benefits of Leviathan's transparent data management. Hash tables are a popular data structure due to theoretical O of 1 lookup time, yet practical lookup time is determined by conflict resolution. Conflicts are commonly resolved via a linked list per hash table bucket, and I've already shown how to implement linked list traversal with Leviathan. A major benefit of Leviathan is that the programmer doesn't have to worry about the size of each linked list node. So let's see how Leviathan performs across a range of node sizes with hash table lookups. This evaluation shows results when iterating over hash table buckets with a uniform distribution. We are first going to look at speedup. Compared to the baseline of performing all lookups on the core, we evaluate Leviathan without padding and mapping support, full Leviathan, and Leviathan with an ideal engine. The first group of bars shows results when the linked list nodes are equal to a cache line, as required in prior work. We see that Leviathan provides a substantial 2x speedup. For smaller 24-byte objects, Leviathan provides similar performance. And without padding, performance significantly degrades because objects frequently span cache banks. When evaluating nodes equal to 2 cache lines, Leviathan still performs well, which is not the case without Leviathan's large object mapping. Now, looking at energy, across node sizes, Leviathan significantly reduces energy both with fewer network traversals and by executing lookups on more energy-efficient engines. And we see that Leviathan's padding and large object mapping do indeed reduce network traffic. The final case study demonstrates Leviathan's ability to support NDC optimizations that require multiple NDC paradigms. Phi is a previously proposed NDC accelerator that treats the cache as a write coalescing buffer. When a core updates data, instead of loading the previous value from memory, Phi pushes the update to the data in the cache. And subsequent updates are coalesced in the same location. When the data is evicted from the cache, depending on the number of buffered updates in the cache line, the updates are either applied directly to the data or logged for later processing, which improves spatial locality. Phi is clearly implemented with a combination of 2 NDC paradigms. Pushing updates to data in the cache is an example of task offload, and processing data on cache eviction is data triggered. Now, Taco, a prior programmable system for data-triggered NDC, implements a version of Phi without task offload. As a result, every update requires pulling data into the core, incurring excessive data movement. Leviathan, however, can fully implement Phi due to its multi-paradigm design. Let's see the quantitative benefits provided by Leviathan when running PageRank with Phi's design. The left graph shows speedup and the right graph shows energy, both normalized to regular push-based PageRank. First, we see Taco when using normal, fenced atomics. Although it does support data-triggered NDC, performance barely improves due to serialization of atomic updates on the cores. When using relaxed atomics, Taco is able to achieve notable speedup. However, this is still with updates executing on the cores. Leviathan achieves additional speedup and energy savings by more accurately implementing Phi using multiple NDC paradigms. And finally, performance is similar to an ideal engine since the NDC actions are relatively simple and short. There's a lot more information in the paper that I'm not able to cover in this talk, so please see the paper for more details. Leviathan builds upon abundant prior work in NDC to provide a unified, general-purpose NDC system. By supporting multiple NDC paradigms and providing a simple-to-use actor-based programming interface, Leviathan paves the way for practical near-data computing. Thank you.